Morning, everyone. Apologies for me running around all over the place getting things ready today. How are y'all doing?
Great.
Glad to hear. Any questions, comments, concerns, etc. before we get started today? All right. Well, we've been talking about Newton's laws and various forces. And today we're going to try to combine all that stuff we've been spending the last week or so looking at together into one big, try to tie it all together. It's early, or it's over. Let's briefly review the laws themselves and the different types of forces we've been looking at. Laws of motion. First law says object at rest stays at rest, or object in motion stays in motion unless acted upon by an outside force. Again, the title for this is inertia. Matter is lazy. Law 2, F equals ma. Very important, very useful formula. Law 3, for every action force, there's an equal and opposite reaction force. We've been examining these through the lens of various different types of forces. Key ones we've been highlighting recently have included gravitational force, also known as weight, mass times negative 9.8 meters per second squared. Normal force, where a surface will exert a force back out of itself if it is acted into. This is what keeps you from falling through the ground. Tension is the force that ropes exert inward on both ends if you pull outward on both ends. Namely, it is worth noting that ropes will pull with the same amount of force inward in opposite directions on both sides. It's always the same number on both sides. And most recently, friction. A force that opposes motion when matter tries to move past, over, or across other matter. And the reason I'm mentioning all of these again is I've created one big example that involves all of them.
Great.
And we're going to spend today looking over this, talking about, again, how all these things work together and how to solve this type of scenario. Here, we have a pulley system. And the function of a pulley is really just to change the direction a rope is pointing. Here, we have one string that is connecting two separate objects. And that one string is tied to both of them. It's the same tension throughout the entire string. The pulley does not change the tension the string is exerting. The pulley just changes the direction of the rope. That is all pulleys do. So rather than both ends being within the same axis, both ends are now in different axes. But it's still the same rope, and therefore still the same amount of tension on both sides of said rope. What this pulley is doing is it is connecting two different masses via a string. One of those masses has a weight of 100 newtons and is just sitting still on a table. The other object is hanging from the other end of the string over nothing. It's just hanging off the edge of the table, supported by the rope. And there's a couple questions that we're going to examine given this scenario. I'm trying to take stock of all my good markers real quick. Now, within this system, one of these objects is currently touching the table. That would be the heavier one right here. And whatever that block is made of, whatever the table is made of, the current coefficients of friction between this object and the table are 0.49 for static and 0.32 for kinetic. So those are specifically the coefficients of friction for this object on this table. So I'm just going to start listing some variables over here. The weight of object 1 is 100 newtons. Weight points down, so I'm just going to make that a negative number and draw a downward pointing arrow. We've been given 2 mu's, not to be confused with mu2, 2 different mu's, mu s 0.49 and mu k 0.32. Those numbers do not have units once again. And the last number that we've been given is the weight of the other object, so Fg2, 50 newtons, also pointing downwards. Before we examine any further, does anyone have any questions about the physical setup going on here? What any of the numbers given represent? All right. Now, first question about this scenario. Usually when something is hanging over the void, it's either going to remain in place or it's going to begin accelerating down. Does that seem consistent with your expectations of reality? So, first observation is this thing is either going to be held in place, say because there's enough friction preventing the system from moving, or if there is not enough friction to prevent the system from moving, this thing is going to start moving towards the floor, as most unsupported objects hanging will do. Now, we've been told here, assuming the system will begin sliding, which type of friction will be present in the system? Kinetic. Very good. What is the definition of kinetic friction? Yes? It's the type that acts while objects are in motion. If the system does not begin moving, say we set this whole thing up and nothing happens, then what type of friction would be present?
Static.
Static, very good. In that scenario, the static friction likely between box number 1 and the table would be enough to hold it still. And if this one isn't going anywhere, neither is the object it is tied to. I want to go ahead and use that to establish something. When two things are tied together, they're going to share an acceleration. Whatever their acceleration is, given that these two objects are physically tied to each other, they will share an acceleration. So either static friction is enough to hold them both in place, in which case the acceleration of both objects would be 0, or static friction is too weak to hold them in place. The tension of the rope will pull this object forward as gravity pulls this object downward. They will both begin accelerating at something that isn't 0. So, regardless of what type of friction is acting, these two objects are going to share an acceleration because they are physically tied together. They have to share an acceleration. If static friction holds everything in place, that shared acceleration is 0. If static friction cannot do that, they will share a non-zero acceleration. They will start moving, and kinetic friction has to take over. So, we are going to operate from the assumption that this system will begin moving. That static friction cannot hold it in place. Kinetic friction will take over, and that means we aren't actually going to need mu s. We are only going to use mu k, because we have identified that once this thing starts moving, this is the type of friction that we will have. Any questions thus far? All right. Now, we have been tasked with finding two things about this scenario. Now that we have established it will begin moving, we will have kinetic friction specifically. We want to figure out the acceleration of this system in this case just meaning all of the tied together moving parts that are going to share an acceleration. The two boxes are tied together, and therefore they and also the string will begin accelerating at the same rate. I want to know what that rate is. We also want to know, what is the tension in the string that causes this to happen? Because the tension in the string needs to be enough to pull this box along with the other one. So again, the two things we're going to be looking for here are A and T. We got to figure out how to make that work. Questions or observations before we continue? Now, we have a nice pre-drawn picture here, and I'm going to ruin it by drawing force arrows all over it. Because again, this is a multi-force scenario. There's lots of different forces here. They're all acting in different directions on different objects. So I find it useful to take our picture and turn it into a free body diagram where we have arrows all over it representing every force acting on every specific object. So I labeled this object box 1. We should make this box 2. What forces are currently acting on box 1 in this scenario, assuming it's going to begin sliding across the table? Assuming it is sliding across the table, what forces are acting on box 1 as that happens?
Gravity, you have normal force, and then friction.
All right. We've established that's going to be kinetic friction. I usually put that arrow like where the object is touching the table. You don't have to do that. That's just something my brain does. You could put it in the middle. That would be fine. Gravity down, normal force up, force of friction backwards. Yes?
Yeah, I was gonna ask, why is the force of friction backwards? Isn't it like pulling forwards?
So, well, what direction is box 1 going to start moving in?
Right.
It's going to go to the right. And friction, by definition, opposes motion. So if the motion points that way, friction points that way.
Okay.
Answer the question?
Yes, thank you.
You're welcome. Now, why is box 1 going to start moving this way?
Because box 2 is pulling down.
Box 2 is pulling on the other end of the rope, and therefore the rope is going to be pulling forwards on this box. So there's one more force present that isn't labeled yet, and that is rope tension, which from this box's perspective pulls rightwards. And that is every force currently present on box 1. Now what about box 2?
Just gravity and
Intention?
Correct. Box 2 isn't on a surface. There is no surface here to create normal force. So there just isn't any normal force on box 2. Its own weight will pull down, and the only thing supporting it is the rope, which is the same rope tied to box 1. And so even though that rope goes over a pulley and changes direction, it's still the same rope, and it's going to exert the same tension on both objects. So I have not specified T1 or T2, it's just T, the same T in both places. How's that feel? This is again because it is the same rope pulling inward on both ends. And it is still inward on both sides. The pulley has just changed the direction that each side is facing, but it's still inward towards the center of the string. Same tension, so it'll be the same variable, the same value. We don't have to find two different T's. It's one tension acting on both objects, just in two different directions. All ropes do this. Again, the entire point of a pulley system is just to change the direction of tension. To kind of give another example of that, pretty often you'll see pulleys employed something like this. Pulleys hanging down, you pull down on this end of something, and the other end of the rope goes up. Does that sound familiar? So, pulleys are often used like this. And again, the whole point here is just to change the direction of tension, because let's say that there's a human pulling down on this end, and a heavy box also pulling down on this end. Tension is gonna pull inwards on both sides, but what inwards means has been changed because of the pulley. It's still inward on both ends. It still has a response to being pulled outward on both ends. The pulley has just made it so that rather than the rope being straight, it is bent. Yes?
So the tension's gonna have the same numerical value?
Yep.
Or,
Tension is going to have the same numerical value on both objects, even though there is different amounts of force pulling outward on both sides. No matter what is happening on either end, tension will be the same on both ends. I could even try to put some sample numbers on this. Let's say human is applying 50 newtons, sorry, 100 newtons of force, and the box on the other side weighs 50 newtons. Tension in this case may perhaps be 75 newtons. It's the same on both ends, even though it's not necessarily the same as either separate force acting on the rope. And conceptually, this would make sense because tension would have to be greater than the box in order to lift it, right? On this end. Meanwhile, on the other end, you'd have to be pulling with more force than the tension in order to actually get the rope moving downwards. If tension was overpowering this person's applied force, the person would get yanked upwards. And that's a bad pulley system. Unless you're like bungee jumping. So, main takeaway from this that we're going to apply over there, same tension on both sides, even if two different forces are being applied at either end. It's weird, but I promise this is how it happens. And we're going to try to demonstrate that over there. Questions? Concerns? Weird pits in your stomach? All right. So, we have at this point identified all of the forces present. There's 4 on the first object and only 2 on the second one. And after identifying these forces, we're going to do what I pretty much always recommend to do, force analysis in each axis, using net force equals blank. Since there's fewer forces on box 2, I'm going to start there. So we're going to analyze first the net forces on box 2. So net force 2 is how I'm labeling that. Definition of net force is the sum of all the forces that are present. And on box 2, there's only 2. We got tension up, gravity down. So those are the only 2 things we need to add together. And what does net force create on objects, according to Newton's second law? Net force causes masses to accelerate, correct? Sorry, you may have said that, my ears aren't great. So, the result of these 2 forces adding up is going to cause the mass of box 2 to begin accelerating. How's that feel? All right. Now, we do know the weight of the box, but we don't know tension and we don't know acceleration. So, We have one equation with the two things we don't know in it. We want these two things, so we're on the right track. But this one equation has both of them in it, so we can't find either or yet. We're gonna approach another two equations, two unknowns type scenario. Aren't those fun? You're allowed to disagree. But our first equation is tension up plus the weight of box 2 down will create an acceleration in mass 2. So we're off to a good start. We have one equation with the two things that we want in it. And that's what analyzing box 2 by itself has told us. So now let's analyze box 1. Now, there's 4 forces acting on box 1. 2 of them are in the x-axis and 2 of them are in the y-axis. And we can't add all of them up, so we're actually going to have to do those 2 axes separately. So box 2 is going to have, box 1, we need to do one version for the x and one version for the y. So we got one for box 2, so net force 2. Separately from that, I'm going to list a net force 1x. That is supposed to be number 1, but I suppose it could spell fix. The x forces on box 1, we've got tension forwards and friction backwards. So those are the x forces present on it. Tension forwards, friction backwards. And within box 1's x-axis, what is the net result of this net force going to be?
You said it again?
Within the x-axis for box 1, what is going to physically happen to box 1 because of these forces interacting? It's being pulled forwards. Specifically, it's being pulled forwards within the x-axis. So what this axis is going to add up to, kind of like how box 2's y-axis, the forces add up to a net force that causes acceleration. These forces in box 1's x-axis are going to add up to its mass accelerating in the x-axis. Yes?
So, like, since they both have the force of gravity, does it not, like, cancel out if there's 2, or it doesn't work like that?
Say it one more time.
Like, if there's 2 boxes and they're both gonna have the same force of gravity, so why can't it just kind of, like, cancel out because they both have the same? Like, wouldn't that just kind of...
If the boxes weighed the same, would the system just not move? Is that what you're asking?
Could you just not consider force of gravity?
Oh, well, gravity is relevant here for 2 different reasons on the 2 different boxes. In box 2's case, gravity is relevant because that is what is trying to pull this whole system downwards. So box 2's weight is very relevant because it is specifically what is going to kind of drive this whole process. If gravity didn't exist, this would probably either hang in place or rise somehow. So box 2's weight is important for that reason. Box 1's weight does not directly contribute to its x-axis acceleration, so we have not actually used that information yet. However, the weight of box 1 does indirectly affect the force of friction on box 1. Why is that the case? Why does something's weight affect the force of friction that acts on it?
The more mass, the more it's in the ground.
The more mass, the more force of gravity, yes. And the more force of gravity, the more what? The more friction in general, yes. The more something weighs, the more friction is going to act on it. But there's an in-between step.
There's normal force.
Correct. More gravity means more normal force. And more normal force means more friction. Right? So, you're all correct. More gravity does mean more friction, but normal force is kind of the in-between explanation for why that is. The more box 1 weighs, the more normal force the table has to exert on it, and the more normal force you have, the more friction you generate. So box one's weight may not be in this formula describing its motion, but box one's weight does affect what this number is. Did I answer the question?
Yeah, so we don't use force of gravity if it's like on a surface practically, or if it has friction.
We don't use force of gravity within the x-axis.
Okay.
So again, right now this equation is meant to analyze the x-axis forces acting on box one, so F1x. And within this axis, net force is equal to the mass of the box times its acceleration, because within this axis, the box is accelerating. Now, separately, is box one accelerating within the y-axis?
No.
No, it is not. So separately, F1y, we would have normal force up, box one's weight down, and those only add up to 0 because the box's y-axis acceleration would be 0. So two different equations for the box's two different axes, and they each create a different result. But this axis does kind of indirectly affect this number, therefore affecting this number. Again, did I answer the question?
Yeah, that makes sense.
Okay. How do you guys feel about this setup so far? Again, right now we're just kind of laying the groundwork. We're describing all the force interactions here. We're going to use them to eventually get to a number for tension and a number for acceleration. Basic premise okay thus far? Okay. Now, these three equations are great. We're going to end up combining them in some creative ways to eventually pull off a two equations, two unknowns scenario and get to answers for those two things. There is one small thing, one quirk we need to think about before moving forward though. Because our goal is to get answers for tension and acceleration. And we know, we're kind of hinging our math here on the fact that we've got the same tension acting on both objects, and they are both going to accelerate at the same rate, right? We're going to hinge our whole two equations, two unknowns argument on the fact that the A's are the same and the T's are the same. There's one small problem with that we have to think about before moving forward. And it's that A points in two different directions for these two different objects. It's the same number for both, but one is being pulled forwards, a positive number, and the other is being pulled down, a negative number. Ordinarily, this might not be a problem, but since we've made them the same variable, I promise the math isn't going to quite work right unless we account for that and add a negative on there ourselves. This, again, your calculator does not have this frame of reference. So we have to add to that frame of reference ourselves. The reason for this is we've plugged in just A for both. And we want the magnitude of A to be the same for both, but because of the pulley thing, A has a different direction in both. And you could actually choose to just switch which one's positive and which one's negative here. But if down is negative, A would be a negative number for object 2. And the math won't quite work right if this axis is expecting A to be positive and this one's expecting A to be negative, unless we add this ourselves to kind of account for that. Yes?
The answer gonna be an equation, ain't
Yeah, we're going to derive an equation first before we derive a number. Is that what you're asking? Okay. Well, right now we've got two equations that have the same two unknowns in them. So we're almost at the point where we can do the whole two equations, two unknowns trick. We just have to figure out a couple small things first. Namely, we don't actually have a number for force of friction or the two masses yet, because what I actually listed in this question was the weight of each box, and we have to work backwards to find the mass of each box, as well as the force of friction. Question so far? Okay. Again, our main goal is gonna be to take these two equations and combine them to do two equations, two unknowns. But in order to do that, we need to make sure the only two unknowns are tension and acceleration. So we need numbers for the last couple things in here first. So, first question then, we need to figure out what the force of kinetic friction on box 1 is. What's the formula for force of kinetic friction?
Normal force times mu.
So you do 9.8 times 0.32.
Almost. Almost. We do want the coefficient of kinetic friction. We established earlier that kinetic friction is going to be the type we're working with, so we're just not going to use the static mu in this case. It's kind of here as a distraction. We're going to use the kinetic mu, and that means we also need a value for normal force. And we've determined, by examining box 1's vertical axis, normal force must be adding up to its weight to be 0. And what is the weight of box 1?
100.
Very good. So n minus 100 equals 0. Therefore, n is positive 100 on box 1. Again, this question went about it a little bit differently. It started by listing the weight of each object, not its mass. That means we already have the weight, we don't have to find it. And weight is what goes here. Therefore, if gravity's pulling down with 100 newtons, the table must be pushing up with 100 newtons in order to keep the box on the table. So n in this case is actually 100. Therefore, the force of kinetic friction is going to be 100 times 0.32. And rather conveniently, that's going to create a kinetic friction of 32 newtons. And that is a number that we can now safely plug in here. Any questions arriving at that number and the assumptions made along the way? All right. One thing to note as we plug that number in, what direction does it point in relationship to our tension? Sorry, what direction does tension point?
Inward.
It points inward to the rope, that is correct. And the way that I've drawn this picture, we're going to call that forwards from box 1's perspective, which means friction points backwards. So if we're just deciding that tension is a positive number, that friction needs to oppose it. So again, your calculator does not have this frame of reference. If they point against each other, we have to add a negative onto one of them ourselves. So formula gave us a magnitude of 32, and we know it's in the opposite direction as tension, so we have to add a negative sign here to make the math work. Formula can't really tell you that because, again, this is kind of cross-axis. I normally recommend having absolute values here. And that means that, you know, the number could be positive or could be negative just depending on the direction of the picture. So I'm going to add a negative here manually to account for the fact it's in the opposite direction as tension. Now the last thing we need in this formula before we move on is a mass for box 1, excuse me. How should we go about finding that?
These are like kilograms, meters per second squared.
That's right. We've got the weight of the box, which is 100 newtons. And by definition, 1 newton is 1 kilogram times a meter per second squared. We know the weight of the box. What is the formula for the weight of an object? Yes. Formula for the weight of anything is its mass times negative 9.8. So if something weighs 100 newtons down, its mass must be something times negative 9.8 to create that much force. So mass 1 should be about 100 over 9.8, which should be slightly more than 10 kilograms.
So you just took the negatives away.
Yeah. This force points down, and this acceleration points down, so I did make them both negative. Dividing a negative by a negative cancels out. I'll show that here, but you get a positive answer.
10.2 over 4.
I'm just gonna cut it off at the 2. Thank you, guys. So the mass of box 1 must be 10.2 kilograms if its weight is 100 newtons. Normally, we've been taking mass to find weight. So we kind of reverse that here. How do you guys feel? Okay. I'm going to take silence as no objections. If you have objections, please tell me, because I don't read minds. I failed that class in undergrad. So that is our mass 1. I'm going to put it in instead of M1. So now the only two variables left are T and A, which again, those are the things we're trying to solve for. So that's every unknown in box 1's x-axis figured out. Now we need to do the same thing to box 2's y-axis. So tension up minus box 2's weight down. So again, then box 2's y-axis, tension is opposing the box's weight directly, and that is a weight of 50 newtons. Since it points down, we're making it negative. That's opposing the tension in this case. And that is equal to box 2's mass times the same value of A, but pointing in the opposite direction. Well, pointing in a negative direction. So we also need to figure out box 2's mass, which the process would be basically the same, but putting a 50 here instead. So M2 would be negative 50 over negative 9.8, and that should be about 5.1.
Yeah.
Thank you, guys. 5.1 kilograms. So that is what we will write instead of M2. And now we have our two equations and our two unknowns.
Can we just divide T minus 32 by 10.2 and then plug A into the top equation?
Yes, we can. At this point, how you, which thing you solve for first is just kind of up to preference. We could definitely, you suggested divide both sides by 10.2 to find A, plug something in here. Yeah, that would definitely work. I am going to do something a little bit different, just to demonstrate that this also works. I'm going to kind of rearrange both of them at once. I'm going to take this one and add 50 to both sides, giving us T equals negative 5.1A plus 50. And then here, I'm going to also add 32 to both sides to give T equals 10.2A plus 32. So I've solved both of them for T. And that means now I have two things that T is equal to. And that means I can set them equal to each other. So, again, just kind of an alternate approach to the two equations, two unknowns conundrum. You can rearrange one of them and plug it wholly in, but you can also rearrange them both for one thing, and then that tells you two things that are equal to each other. So I'm going to take that over here, running out of board space. Negative 5.1A plus 50 equals T, and we know that T is also equal to 10.2A plus 32. two things that are both differently equal to t, and that means due to the commutative property that they are equal, or the associative property, one of those properties, that they are equal to each other, which means we can kind of cut the middle part out. And just directly skip to negative 5.1a plus 50 equals 10.2a plus 32. Thus eliminating one of the unknowns, and now we can solve for acceleration. That's a different way to do two equations, two unknowns. How does that feel? And any questions arriving at this point? Again, there's more than one right way to work this out. You could choose to do it one of the older ways. I'm just demonstrating a modified tactic. I want all the accelerations on one side and all of the not accelerations on the other. So I'm going to send the 32 over and bring the 5.1a over as well. That would look something like 50 minus 32 equals 10.2a plus 5.1a, since the signs swap. That would be 18 equals
15.3.
Thank you again. And so the magnitude for A would be 18 over 15.3, so a little more than 1.
1.18.
1.1, sorry.
7.6.
Thank you guys, I'm going to round that to 8. And what's the unit for acceleration?
Miles. That's what meter.
Very good. So that is the unified magnitude of acceleration for this whole system. And notice that it is accelerating. That means once you release it and it starts moving, everything's going to get faster and faster until this thing hits the floor. Similar to falling, it's an acceleration, but not quite the same rate as falling. If this rope was cut, box 1, box 2 would just fall. Instead, tension in the rope is slowing it down. If it was falling, it'd be accelerating at negative 9.8. Instead, it is accelerating at this rate because tension is slowing it down. Again, kind of like a parachute or a bungee cord. Now that we have acceleration, you can pop it into either of these two things to find a value for tension. We're about out of time, so I'm just going to skip to that number real quick. I'll just use the other one. We are out of time. You can back up. I'm just going to find the number so you can write it down.
Is it 44?
It is 44. Thank you. You beat me to it. The tension in the rope, and again, this is acting on both sides, is about 44.04 newtons. That's the answer for tension. Note that that is not enough tension to hold this one up. Its force of gravity is greater. But it is enough tension to overpower the force of friction that we found. Again, creating the effect of both objects accelerating. So, same tension, but it's not the same as either force acting on either end. It is okay if this was confusing. The whole point is we're practicing it. So let me know if you have any questions. Do be working on the homework, and have a nice day.